So, last time we were in the middle of talking about making a queue, but with an array. We saw the linked queue. The linked queue really wasn't too bad. But we saw this issue with the array implementation because, with the linked structure, we could remove things from the front and there's really no, whatever, it's inconsequential. We just remove things from the front. But with the array, we see an issue. With the stack, the array wasn't an issue because we always add and remove from the one end, the end that's like growing and shrinking it. And 0, the index 0 was always the bottom of the stack. But with the queue, we've got a problem where, because we're removing from the front, we've got this issue of this empty space. If I remove the thing at index 0, what do I do with that empty index 0 now? Do I move everything down one? Do I just leave it the way it is? I don't know. We looked at two ideas. The first idea was move everything down. You remove something from the front, move everything in the queue down one such that if it was at index I, it becomes index I minus 1. But what was the downside to that? Who can tell me what sucked about that idea? Yeah. If I had n things, how many things do I have to move down? All n. It sucks. So, in the linked implementation, it was constant time. But with this array implementation, we now have this linear time thing removed from the front. It's terrible. So the solution we had was, just keep track of what the rear is. Or pardon me, keep track of what the front is. So instead of the front always being at index 0, just allow the front to change. So if you remove the thing at index 0, update front to be index 1. Problem solved. But what was the what was the drawback of that idea?
The array is just going to take up progressively more and more space.
Yeah, we've got this empty spot at the beginning. Right? With the first idea, if I had n in queues, followed by n dequeues, by moving everything down, I could do another in queue, and it would be whatever, it's fine. Right? It just goes to index 0. But with the second idea, if I do n in queues and then n dequeues, I've got all this wasted space. And the next time I add something, I have to do an expand capacity. Both ideas are going to require an expand capacity thing. But, I don't know, we got this funny issue of that wasted space in the front, which maybe really not that big of a deal, but you can't help but feel like we're wasting space. So here's the third idea. Pretend the array is a circle. That's it. That's the magic. Keep track of the front, keep track of the rear, keep track of the size. If there's any empty indices before the front, so let's say the front is index 7, meaning if we're thinking of idea 2, indices 0 through 6 are empty if the front is index 7. So then when I in queue again, let's say I get to the end of the array. My array is size 10. I want to add that 11th thing. There is no index 10. What I do, just loop back and go to index 0. Set the rear to 0. That's the trick. Now, though, I don't expand capacity when I hit the end of the array. I expand capacity when there's just, it was the same rule as before, when there's no more room in the array. It's just the rear might not be the length of the array minus 1. The rear might be overlapping with the front. So the idea is this circular array idea. There's no such thing as a circular array. That doesn't exist, but we're going to pretend it does. So here's an example of an array with 100 array cells. 100, it's got a capacity of 100, but there's only 4 things in it. And it just so happens that the front of my queue is stored at index 98, And the rear is at index 2, because remember the rear is always the next available spot. When I NQ, it just goes to index 2 and you increment. But the values here, the order of the elements would be index 98, 99, 0, 1. That's how it goes. It's contiguous that way. But it's more abstract. So the idea is my indices go 0, 1, 2, 3, yada, 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 n minus 2, n minus 1, 0, 1, 2, 3. It just keeps looping. When you would go to that nth thing, okay, n minus 1, the thing after n minus 1 is 0. Remember, it's a length n and index 0 exists, right? So we always just loop back to the beginning. That's all. That's the trick. It's really not too complex. But yeah, what comes after n minus 1 is 0. What comes before 0 is n minus 1. We just pretend these indices just work like this. So here's an example of an array where I've got a front and a rear. And then what do I say? After a couple DQs, this is what it looks like. After a couple NQs, this is what it looks like. Right? Do you see? Any questions about this idea? Yes. You sure?
Sure.
Come on. All right. So at this stage, you're probably thinking, okay, that's not too bad. We'll need some logic here, though, right? We'll need to do some logic where we say, okay, if the value is bigger than the length of the array, we have to loop back to like 0, right? We have to have logic there to account for this. But it's actually even simpler than that. But it requires that we have a good understanding of a special operator called modulo. We use this in 161. Who here remembers what we used this for in 161? It's pretty early in the semester. What do we use it for?
To check if the value is even.
Exactly. To check if a value is even. And the way we did that is we would say value mod 2. And mod 2 means divide this number by 2 and tell me the remainder. If the remainder of doing a division by 2 is 0, what does that tell you?
It's even.
It's even. If the remainder is 1, it's off. We're going to use this exact same idea, but not to check if a number is even or odd. We're going to check if the number is like divisible by the length of the array. So 4 mod 2 is 0, because 4 divided by 2 is 0, remainder 0. 5 mod 4, well, 5 divided by 4 is 1, remainder 1. So 5 mod 4 is 1. 7 mod 8 is, well, how many times? This is the question you always have to ask, right? And when we're doing division, we're doing like integer division here. We're doing division like it's grade 2. When you learn about remainders, right? No decimals or anything here. I ask, how many times can I take 8 out of the number 7? How many? 0. No. Once. 0. I can't take 8 away from 7. But what's the remainder? 7. Yeah. Now look, let's go back to the other one. 5, 4. How many times can I take 4 out of 5? Once. Remainder 1. That's the question we're asking, right? So, this is the magic trick. Whenever we need to update rear, we do rear equals rear plus 1 mod the length of the cube. Let's think about this for a second. I think I've got an example here. Let's just work through this example. Assume I have an array of capacity 10, and rear is currently 9. All right? So rear is at the end. Rear should always be, oh, actually, I guess we have an issue here. Rear is 9. Rear should always be at the index of the next available spot in the array. Right? So whenever I add something, it should go to index 9 here, I guess. If NQ is called, the new element is added to index 9, the rear. Nothing new is going on at this point. It's all fine. But rear, if we increment it, it would become 10. Right? But there is no index 10 in an array of length 10. We have 0 through 9. So if rear is supposed to be referencing the next available spot, and rear would get incremented to be 10, we've got a problem. There is no array index 10. But the length of that array is 10. And because of this looping thing we want to do, the next available spot, assuming it's empty, would be index 0. Because of this looping thing. Because we're out of room at the end, we got to loop back to the beginning. But here's the magic. If rear is 9, I add 1 to it, it becomes 10. What is 10 mod 10?
0.
How many times can I take 10 out of 10? Once. What's left over?
0.
Rear equals rear plus 1 mod the length of the cube. This will always work. This will just do the looping for you. There's no need for any if statements here at all. There's no logic you need to deal with of like, okay, if the rear is greater than the length, I need to say rear actually equals 0. No. This little mathematical expression does that for us. It's phenomenal. It's great. We love it. But let's work through it again. Let's say rear is 6. I NQ something. Let's do that expression. So rear equals rear plus 1 mod the length of the cube. What's 6 plus 1?
7.
What's 7 mod 10? How many times can I take 10 out of 7? 0. Who said once?
Sorry, I thought you were confused.
Which number goes where? Yeah, I get it. I can't take 10 out of 7. There's just not enough there. What's left over? 7. Whenever the number is less than the length, whenever the number is less than what it's being modded by, it's left alone. It's only until the number is equal to or greater than where mod will do anything. 6, incremented, becomes 7. 7 mod 10, well, I can't take anything. It's remainder 7. It's great. It's always going to be left alone because if the number is less than 10, that means I can't take 10. I'm saying 10, but really I mean the length of the cube. I'm using 10 as a concrete example. If the number is less than I don't even know what you call that on the right-hand side. Divisor doesn't make sense, right? Because it's not really, maybe it's divisor, I don't know what you call the operator.
Technically, it would be considered divisor.
It kind of is.
Modular, I guess.
Well,
There's a more complicated word.
Right.
I don't know it off the top of my head.
because it's,
But
yeah.
divisor works.
The thing we want to divide by to get the remainder, if the number I'm trying to mod by is less than the number I'm modding by, I can never take any numbers out of this. I can never take 10 out of any number less than 10. I can't. So the remainder is always going to be just itself. So that's where the magic happens, this modulo. Modulo isn't just for checking if something is even or odd. It's for checking what the remainder of something is. If the length of the array is 10, and the next available spot would be index 10, which doesn't exist, well, 10 mod 10 is actually 0. So it loops back to the beginning for us. It's magical. Now this is the update for the rear. Would I need something similar for the front? Would the front ever need to loop back?
Yeah,
Of course. I try to trip you up.
eventually.
Eventually, of course it could happen. Right? Yeah. So that example there just worked you through it. So, does the strategy for updating front need to also be changed? Yes. Will this circular array ever run out of room? Yeah, it will. Because there's going to be a point where if I have an array of size 10, if I want to have 11 things in that queue, well, there's just not enough spots. So I'm going to need an expand capacity. But the expand capacity for the circular array is going to be a little complicated. No, complex. Let's call it complex. But we'll get there in a moment. So here's a bit of a warning. Now, this warning isn't really that applicable to this particular scenario. We talked about 3 implementations. The circular array implementation has some added complexity to it, and really it's going to come from kind of like expand capacity, just the circularness of it kind of throws off. But it's not too bad. And really, we should probably use this circular implementation if we're implementing an array queue. But in general, there is this idea of premature optimization is the root of all evil. It's a quote from Dijkstra, who's a very famous computer scientist, where sometimes we can get so focused on improving our implementation to make it better, to make it more efficient. We get so focused on it that we lose sight of what's important. If I spend 20 minutes coming up with a quick and dirty solution for a problem that I need to find a solution for once, or a day and a half coming up with a beautifully elegant solution that runs twice as fast that I still only need to calculate once, and the runtime went from 5 minutes to 2.5 minutes, what's better? The first one, probably. If I don't need, sometimes good enough is good enough. Sometimes. You might come up with a beautifully elegant solution that is complicated as hell and no one's going to follow it. And was it worth it? How often is it going to get run? Is it really going to matter? Maybe it does. Maybe it really does. Maybe it doesn't. So this is an important thing I want to emphasize. If you're writing your code, and the reason I'm bringing it up now is not to really say like, oh, maybe the circular array is too complex. That's not the message here. The message here is we're getting to the point where we're thinking of nuance of implementation. And I'm saying not always should we be always looking for that little trick we can pull off. Because sometimes that trick, forest for the trees type thing. We get so focused on my solution's better. And it's like, great, but it's assignment 1. And no one gives a shit that your solution ran just a little bit faster. You saved a couple floating point operations on your processors compared to the person you're sitting next to. No one's going to care. And I don't mean that to dismiss the elegance. I mean that as don't focus so much on these beautiful, elegant solutions when sometimes good enough is good enough. And often, a lot of times, people focus on getting these beautifully elegant solutions to these. Look, when you're solving a problem, you're solving a few dozen sub-problems together to solve a big problem, right? That's programming. And they cascade, right? If I solve one of these sub-problems with a beautifully elegant solution, it takes me twice as long, maybe it takes a day to implement and it took you 20 minutes to implement. But mine is beautiful and glorious. Great. And I made it run 10 times faster. But that is only a tiny piece of this big overarching thing, and 80% of the runtime comes from this part of the code. No one gives a shit. That starts to turn into like programmer navel gazing, where they're just like getting so excited of their code when it's like, okay, now you're just wasting people's time. It's like you're flexing to yourself. You think you're flexing to other programmers, but no one really cares. That's not to say good optimization is not good. I'm not saying don't optimize. That is not the message here. The message is you gotta be aware of what you're going for. Just be cognizant of sometimes good enough is good enough.
Would you accept good enough is good enough on the assignment?
Well, maybe.
So your entire rant was pointless.
It depends. No, it depends. Here's a queue. Front is 2, rear is 1. It's not full. Obviously, this is a small example. Count as 3, it's great. It's great. As soon as I in-queue something, we now have front is 2, rear is 2. The next available spot would be index 2, but of course we're out of room. And we need to call expand capacity. But remember, the front of this queue is the thing at index 2. If I did expand capacity like we've done every time before, I would get something that looks like this. Ignore the light blue things. The expand capacity we did before, we said, okay, start at the beginning and copy everything over in place, and all the extra room we added was added to the end of that array. But we got a giant problem here, don't we? The front is index 2. The thing that comes after the front is the thing at index 3. The thing that should come after the thing at index 3 should be at index 4, but it's not there. It's at index 0. This is a problem, isn't it? It's not going to work at all. We've introduced a giant gap in our sequential data. That's not admissible. That's not workable.
Also, Leo is still 2, so it doesn't even work.
Yeah, and so like if I were to add something in rear, it would overwrite the thing at index 2. We got a huge problem if we did it this way. This is a terrible idea. We need to expand capacity. We need a bigger array, but the expand capacity, excuse me, the expand capacity we use for the course list, the expand capacity we use for the contact list, the expand capacity we use for your country catalog, for your stack, not going to work here. You can't simply start at the beginning and copy everything over from index 1, index 0, index 0, index 1, index 1, index 2, index 2. We can't do that. We have to be a little bit more creative. This could work, right? This would totally work. Right? Somehow we copy things over such that, okay, the front goes to index 2, the thing after go to index 3, and then the thing that wasn't index 0 goes to index 4, where it should be. The thing after that, index 5, and then the rear would be index 6. This works. This entirely works. This is a great solution. The one we're going to use is this. It's basically the thing before, but we take the thing at the front and add it to index 0. It actually ends up being easier this way. It becomes a little easier to, in my opinion, it becomes a little easier to reason about and implement if you do it like this. Because with this one, imagine I have this. I start at index front and copy it to index 0. Front plus 1, I plus 1. Front plus 2, mod the length of the array. Always mod the length of the array here, actually. I should have said that for the previous two. Front, mod the length of the array. Front plus 1, mod the length of the array. Front plus 2, mod the length of the array, and copy it into index 0, 1, 2, and so on, and so on, and so on. So it actually becomes a little easier to implement, in my opinion, if you do it this way. And it's not only implement, but to reason about, because at the end of the day, you always start with 0, the front's back at 0, it's nice. It's not required, a solution like this, and this is actually kind of the beauty of expand capacity. Both solutions would work. Both are private methods. If I gave you a working solution of an array queue, that works, it passes every unit test, and you use it a billion times, and you know it does exactly what it does. Do you care at all which version of the expand capacity it was? It's not, it doesn't matter at all. It's inconsequential. It worked. It's a private method. Yeah?
Wouldn't this, like, eventually, if it ran enough times, wouldn't you have a bunch of empty space at the front of the array, and that would, like, take up more space? Or, like that there?
Well, we're not going to do this one. And there would be, but eventually, if we did more in queues, it would just loop back to the beginning anyways, so it wouldn't matter. But good observation nonetheless. Cool. Any questions about this idea so far? So, will this implementation work? Of course it will. Just like the previous two implementations, they would work. They're all priority queues. I keep calling it a priority queue. It's on my mind for whatever reason. Queue, array queue. Excuse me. What's the computational complexity of an in queue now? Well, the in queue is easy. It's just like the other one. It's constant time We might have to do expand capacity, maybe. But when we don't do expand capacity, it's constant time. You just add it to rear, and then you increment rear, mod the length of the array. DQ is also constant time. You just remove the thing from index front and increment front, mod the length of the array. Both are now computational complexity index 1. My brain is not working today. Computational complexity constant time. And sure, we still have to expand capacity, but you know, we don't have that issue of wasted space anymore that we had in idea 2. We just kind of like improved idea 2 by allowing us to loop back to the beginning with simple basic arithmetic by using remainder. Pretty nice. So here's an example of an in-queue. Now it uses a couple of private methods that I had implemented. If you go download this implementation, there's a couple private methods. And do I include them here? I do. Next index. I just wrote a little private method to do that arithmetic for me. I give it an index and say, well, its current index plus 1 mod the length of the queue. This is what I showed, like rear equals rear plus 1 mod the length of the queue. But here I generalized it with a method to take a parameter and just return what it would be. Do you see what, like, does it make sense what this method is doing? It's just doing that increment for me, and it'll automatically do that looping back to index 0, whatever. You might say, was it necessary? Let me put it this way. I replaced one line of code. Like, well, line 44 could say rear equals rear plus 1 mod the length of the array. It could say that, but instead I made it a method call. And look at all this extra space I needed for that method call. Who could tell me what my motivation was for making this a method, though?
In case you had to use it in other points of the code?
Absolutely, and I will. I'm going to need that. But I am going to need it for updating the front as well, in addition to the rear. But then again, every single time I'd be replacing one line of code with another one line of code that's just the method call. So why else?
It makes your code more clear.
I think so. If I'm a programmer, and I'm not really sure how you're doing this and what's going on, and I see rear equals rear plus 1 mod the length of the queue, yeah, based on my experience as a programmer, I might know what's going on there. But if I'm a programmer and I see rear equals next index of rear, maybe it should be subsequent index, I don't know. But I see rear equals next index of rear, suddenly I go, oh, this is just, okay, it's getting whatever the next index should be. It's updating the index. Great. To me, I think this is a little clearer. Maybe you don't agree. Code it however you want. Point I'm making here is my coding decisions are not solely based on getting the code to do what I need it to do. It's doing that while also being very aware of what does the code look like. Has anyone found themselves doing that yet? Where they wrote a function, or they know they need to do these two operations, right? And they left going like, how do I want to do this? Right? I could do it this way, or I could do it that way. What's better? What's clearer? And yeah.
Do it like all the time.
Yeah.
On.
Honestly, I spend a lot of time thinking about the code layout and what the code says. And if you don't find yourself doing that yet, you will. If you are a good programmer, you're going to start to take the time of like, right? I increment size. Would it make sense to increment size beforehand or after? It doesn't matter, but what's a little clearer? Well, let me put it, here's my train of thought. I go, here's in-queue. Okay, I've got my expand capacity check. What are the steps I need for in-queue? Okay, add it to the end, update the rear, update the size, whatever. I could have updated size before setting the queue rear, right? I could have done that. But to me, I don't know, I just didn't like it. It wouldn't, to me, it doesn't make sense to update the size before I add something. Even though this is a method call, and it's going to be inconsequential if I updated the size before actually adding the thing to the array, it wouldn't matter. But I don't like it like that. It just makes more sense to update the size after to me. Why? It doesn't make sense to do it before, I guess. I don't know. It's the way my brain works. And I spend time thinking about the order of these lines of code. Even though they might be inconsequential, I just think it's a little clearer this way. Maybe you don't. I do. So yeah, next index, great. Expand capacity. So what's going on here? It's actually quite nice. Create the new array, index I starts at 0, goes to the length of the original Q. So the field Q. Now we're going to use the index I to index the new array because we want the things to start at index 0, 1, 2, 3, and so on in the new array. So that's why when you see new Q, you have index I. But you'll notice that the old Q, the actual field, called Q, is starting at front. And front gets updated each time with that next index call. So I updates and front updates, but the values of them will differ because this one has to go back to 0 and whatnot eventually. So that's it. The only real difference between what you saw before was this is not an I, and we didn't need this updating rule for front. When we're done, we make sure, front's going to be some arbitrary value based on wherever the front was before and what the rear was. Front is 0. Rear is, well, the size now. And Q field is, well, the new Q. So that's the expand capacity.
I assume in the for loop when you put plus plus I, it's supposed to be I plus plus.
It's not supposed to be, but so there's a funny story about plus plus I. Classically speaking, plus plus I is faster than I plus plus. In reality, it's not. Because of optimization and compilers and whatnot, it knows. Now, the reason is when you increment I, so when you say I plus plus, that means execute this line of code, and then the last thing you're going to do is increment the value of I. Right? Now, when you see it in the context of a for loop, it's a little different. But if I have a line of code that says I plus plus, it just means effectively run that line of code with what the value of I currently is, and then increment it. Now, when you just see I plus plus, all that's going to happen is it just gets incremented. But really, I could be doing multiple things on that line of code. So what ends up having to happen is the computer needs to store the value of I beforehand. So it needs to store this extra information, where when you have plus plus I, it means increment I, then run this whole line of code. So there is a difference.
If you implement I in this situation at the beginning, wouldn't I then be 1 at the start of this?
No, it wouldn't. It still wouldn't matter because it's the last line of code after everything runs, just based on the syntactic sugar of the for loop.
Okay.
Interesting question though. Here, if I were to say sum at index I plus plus, and I equals 7. The line of code for would give me the thing at index 7. If you were to write, and this would work like this in Java. If you were to write this would give you the thing at index 8. Because it increments I, and then computes the rest of the line of code. So which side the plus pluses are on actually dictates when that value gets incremented. Here's my piece of advice. Don't ever do this. Look, if we had, let's say I had something like a cube, a stack. Right? And I wanted to add something to the stack at some index. Right? I could do this in one line of code, where this one line of code says, okay, take the element, store it at index size of the stack, and then increment size. Maybe it should say top, not size, because that's the name of the field we used. There. This would be a line of code that would totally work in the stack implementation. This means take the stack, store at the index top the value of element, and increment top after everything is done on that line of code. Who can tell me why I hate that line of code?
Everything's all condensed into one line and it's going to be hard to read.
Yeah, is that what you were going to say? There's a lot going on in that line of code. Sure, okay, two things. There's two things. I am saying store the element and increment I in one line of code. Fine. But you know what's a little clearer to me? There. That's a little clearer. Add the thing, increment top. Now there's no guesswork. Now there's no multiple steps taking place on a single line of code. This, to me, a little clearer. So, I actually was going through and updating all of these plus plus i's to I plus plus just because I tend to not like to focus on this despite focusing on this right now. This syntax is entirely correct, and you can go talk to some programmers today who will insist that plus plus I is the right way to do it in a for loop. They are wrong because it's not 19 whatever anymore. Compilers will optimize this such that it'll just do it the faster way for them. Oh, so the point I was making, when you do plus plus I, you don't need to store the value of I before and after, you just increment I and then use it. So there's no extra steps of like setting something to a register in your CPU and then incrementing it after, and you just update it and go. So it actually saves a couple of floating point operations on your computer. Oh my God. It's actually amusing. It's actually quite funny that you brought this up because only a couple days ago, has anyone, probably not, I think I asked this already once in the class. Has anyone seen the YouTube channel Code Aesthetic? His latest video talks about plus plus I exactly, and he makes fun of.
I gotta see it.
They actually make, I actually recommend this video because I thought it was quite amusing. Where they show, even if it's 19 whatever, and your compilers don't optimize your code in terms, let me make sure I'm very clear. You write your code, you compile it, traditionally speaking, you compile it into the zeros and ones that run through your processor and the hardware on your computer. Okay? Depending on what my code says, it can impact what the zeros and ones say. What the 0 and 1s get turned into that go run on your computer. And if I can configure my code such that the 0s and 1s can do something in a faster way, we should do that. The good news is modern compilers will look at your code and be like, okay, look, that's great, that's great. I'm going to change it as I'm compiling it because I know better and I know that I can compile it and arrange the 0s and 1s in a way that you didn't explicitly say,
But it does work.
but it's going to work and it's going to be better. And that's called optimization. And the reason we love this, now in a lot of programming languages you can turn on and off optimization and actually set it to different levels of optimization. But the reason we like this is it allows us as programmers to write our code in a way that can be very clear, but perhaps verbose. And if it was directly compiled to what would be running on your hardware, it might actually be slower. But the code that we write is for other human programmers. It's the compiler that takes that to something the computer likes. So whenever you hear someone say like, oh, code, that's like computer speak. Well, no, that's actually like human speak that's easy to translate to computer speak. Right? So these optimization things built into the compilers do a good job of, it allows us to write our code the way we like it, and then it can do the optimization in the back end. So Anyways, in the video, he goes to show, even without the optimization turned on, the amount of difference it makes is like a nanosecond. And during the discussion about it, he counts the total number of nanoseconds. And you'll see. If you watch the video, I recommend it, it's fun. But that is something I should change. All right, span capacity, whatever. Okay, DQ. Here's the DQ. Take the thing from the front, update the front, decrease the size, because of course we just removed something, and then return the element. Remember that private helper method, next index, does the wrapping for us. I don't need to think about it anymore. It's great. Equals. Now equals is a little hairy, because what does it mean for two Qs to be equal? First of all, let's talk about what would it mean for two Qs to be equal. And I'm not talking about array Qs, I'm talking about the Q data structure, two abstract Qs. How should we define two Qs to be equal? To me, it would make sense if the things at the front are identical, the things at the front are deemed equal, the things after them are deemed equal, and the things after them are deemed equal, and so on, and so on, and so on, and so on. And both Qs have the same number of things, and everything in them are the same in the same spot. Does that seem reasonable to you? But who can tell me where the problem is going to come in with these array Qs?
The order might be the same, but the font would be different.
The orders and the elements might be exactly the same, but where in the arrays they are could be entirely different. One might have the front end index 0. The other might have the front end index 72. And it loops back to index 0. It's a little hairy. But don't worry, with some simple, by taking our time, pretty easy peasy. What are we going to do? Okay, are they literally the same thing? Are they literally aliases? Okay, if they are, they're equal. If 0 is null and the other thing isn't even a Q, they're not equal. Great. Otherwise, create an array Q, check their sizes. If their sizes aren't the same, they're not equal. So if we ever get to this line of code, we now know they both have the exact same size, right? So this current index variable starts at this is front. That current index starts at that front, where that is the reference variable to the other one. So I have these two variables that keep track of the indices that we're comparing in both respective arrays. But they could be entirely different values, and that doesn't matter. Then all I have to do is loop through the size, because they're both the same size, we've established that. So I could have said this size or that size, it doesn't matter. Check their size, or we check their size. Loop size number of times. The actual value of I don't care about in this code. All I care about is that it's going from 0 to the size, -1. If the objects aren't equal at their indices, their respective indices, starting at the front, then they're not equal. If they are equal, keep going. And look how I'm updating the indices. I'm saying this dot next index, that dot next index. Is it important? Here's a thought question for you, a good question to gauge your understanding. Take a moment and think, is it important that this current index uses this is dot get next, and that current index uses that dot get next? Or does it not really matter? Could I have used this dot next index and this dot get next index for both?
No. It does matter. No, you can't use it for both.
Why does it matter?
Let's say this current index stuff, the font for that one was 5, and the font for the other one was 3.
Yeah, but
They'll index completely to two completely different positions.
But this current the next index takes a parameter of this current index. I could give it whatever value I want, and it should just increment.
But it needs to increment based off of the array that you're currently using.
So it's the looping and the length of the array that matters.
Yeah, in other words.
this Q array might be size 10, and that Q array might be size 100. So that mod part, where I say mod, the length of the array, well, which array it is really matters. So yes, it very much is important that we use this next index for this current index, and that next index for that current index. Because those private methods make use of the length of the arrays within their respective instances. And then, anyways, after that whole loop, if I ever get to the end and we never return false, I can conclude they're equal. So the trick here was, with the stacks it was easy. Start at index 0 in both arrays and go. Right? It was easy. With the queue, it's a little different because the fronts might be entirely different indices. But you can see that this actually wasn't too bad to account for in the code. Yeah, great. Great. And if you took this plain code, oh no, this is also a mistake. This should say array, plain linked queue. Oh my gosh, another bug. This is wrong. But the good news is, because they're both queues, I could fix this by changing that one line of code. Line 6, is it? If I just change the right-hand side of line 6 to say new array queue, all of this code will work just as if everything was fine. Cool. Any questions about any of this array queue stuff? Okie dokie. All right. See you later.